For question 1, although the question says, explain what is meant by an isotope, the only way you can really answer this question is by talking about a pair of isotopes of a particular element. And in fact that's what the mark scheme does. It compares two isotopes of an element. So you must mention that isotopes of an element have got the same number of protons but different numbers of neutrons. And to get 2 marks you must mention both the protons and the neutrons. Even though using the word element means that you are talking about the same number of protons, don't leave it to chance. Mention it explicitly, the same number of protons. Some people, by the way, fell into the trap of suggesting that an isotope was an unusual form of an element. Well, that isn't the case. Every form of an element is an isotope, so you've got some common isotopes, or the normal ones, and you've got some rarer isotopes. But everything is an isotope. Part B gives you a table, and it says it's about 2 isotopes of uranium. So the first thing you have to do is to write down the unit for specific charge in this column. Now, specific charge just means charge divided by mass. And since the charge is going to be measured in coulombs, and the mass is going to be measured in kilograms, charge divided by mass will be measured in coulombs per kilogram. And there's 2 ways you can write it. You can write coulombs slash kilograms, that's okay. Or you could write coulombs kilograms to the -1. That's also alright. But what you must not do, as some people did, is to try to be too clever and do both. If you write coulombs slash kilograms to the -1, that's wrong. So you go for one or the other. Next mark's easy. In the above table, write down the number of protons in the second isotope. I have to remember, what is this table about? Well, it's for 2 isotopes of uranium. So if it's 2 isotopes of uranium, isotopes have got the same number of protons, so it's got to be 92 protons. B part 3. Calculate the specific charge. So quite a few people seem to be having problems still with specific charge, so let's do this example. Right, specific charge means charge divided by mass. Now it's perhaps a little bit misleading because here it doesn't make it obvious whether you're supposed to be dealing with just the nucleus or with the whole atom. An isotope, the word isotope actually refers to atoms. But if we were dealing with an atom, there wouldn't be any charge, there'd be no point asking the question. When we go back to the table does say specific charge of nucleus. So we're definitely dealing with the nucleus. So specific charge is charge divided by mass. Charge divided by mass equals, well, what's the charge? In the nucleus, it's the protons that have got charge. How many protons are there? There are 92 of them. How much charge does each one have? Well, the charge on a proton is the same as a charge on an electron, which hopefully you will remember. If you don't remember it, you have to look it up on the data sheet, which is there. Charge on electron. For electron, it's given as minus 1.60 times 10 to the minus 19 coulombs. Obviously, proton is plus. So 92 times 1.60 times 10 to the minus 19. Divide by the mass of a nucleus. Well, what is there in the nucleus? There are 92 protons, and each proton has got a mass that's given on this sheet, 1.67 times 10 to the minus 27 kilograms. But that's not the only thing in the nucleus, because also in the nucleus that's also got mass is 143 neutrons. So 143 times, what's the mass of a neutron? Look at the mass of a neutron. It's also 1.67 times 10 to the minus 27 kilograms. Obviously on the data sheet we could have used an extra decimal place for each of those, but there's no point because we're only dealing with 3 significant figures in that part of the question. So if we work that answer out, 3.8 times 10 to the 7, and it's coulombs per kilogram. Now because if we just work into 3 significant figures, the mass of a proton and neutron is the same, you could of course have just added those together and had 235. You still got the same answer. For the last part, we start off by knowing the specific charge, or the charge to mass ratio, and we know the charge and we're trying to find the mass. So, charge over mass, that's the specific charge that we know, it's equal to 3.7 times 10 to the 7. And how do we work that out? Well, the charge, 92 times 1.60 times 10 to the minus 19, that's the charge, divided by the mass. Well, we could treat the protons and neutrons separately, but it's easiest just to treat them as the same. So what we're trying to find out really is how many protons and neutrons are there altogether. So call that number A, number of protons and neutrons altogether. You could call it X or anything else, but A is the thing we usually use. And what's the mass of each proton or neutron? What we've just been using up there, 1.67 times 10 to the minus 27. So we can now rearrange this equation to find A. Because A must be equal to, so forget the bit I've written down there. If I move A up here and I move that down there, A is 92 times 1.60 times 10 to the minus 19 divided by 3.7 times 10 to the 7 times the mass of a proton or neutron, 1.67 times 10 to the minus 27 . 238. So A, that's the number of protons and neutrons added together. So number of neutrons is 238 minus the number of protons, which was 92, which equals 146, which you put in the table. Now you might have got an answer of 147 or 148, depending on how you did your rounding. And the examiners would have accepted all those, because really, they're at fault here. They're trying to get a number with 3 significant figures, and all they've given you to work with is a number that's got 2 significant figures. So really, this data isn't really accurate enough for you to find the number of neutrons exactly. Bit of a dodgy question, really.